Good morning, everyone, and welcome to our first talk of today. Its title is Enumerative Geometry and Quantum Torus by Michael Polyak.
Hi, it's a pleasure to be here in Miami in this sunny morning, wherever all of you are. So basically, the whole story is about the following. So let me start from just a simple problem, or one of the most common, is to count the number of, say for simplicity, plain rational curves of a fixed degree passing through a certain fixed collection of points. Now, this number, it's known that it depends only on the degree of these curves and not on the choice of points, as long, of course, as these points are in generic position. So what was known until the 90s was, well, an obvious thing about n1 equal 1, which is just the number of lines through 2 points and then the number of conics through 5 points. But then there were, of course, 19th century results about the number of cubics, and then the degree 4 and 5 already as late as just the 90s. Now the situation changed significantly when Kontsevich just found some certain recursive formula. It doesn't matter what exactly this formula is, it just calculates for you this number of curves using these known numbers for lower degrees. Now, it's just the problem with it is that it uses an extremely heavy machinery. So, of Gromov-Witten invariants and all these Witten diagram filling the equations for the potential. And it's rather hellish. So, in particular, it uses quantum cohomology and other stuff. So, an obvious question is, are there any simpler ways to reproduce these results? And also, maybe some simple, hopeful, even combinatorial ways to obtain new results and in a similar field, along the same lines. Some enumerative passage tangency problems. So a nice setup for this is that of tropical geometry. So tropical geometry is some kind of piecewise linear version, or skeletonized version of algebraic geometry, and it's rather combinatorial and uses just polyhedral structures. So I will not talk, give for you a complete introduction. I will rather just sail through within 2 minutes. If you didn't know about it, you will probably not know now anyway, but if you did, you don't need it anyway. So the initial approach was using amoebas, and amoeba is some kind of simple mappings from the complex plane to the real plane, where you just take the log of the absolute value of both variables. But when you take the log, you fix a certain base of this logarithm, and as long as this base is fixed, nothing interesting happens. But when you vary it, then interesting things start to happen. So if you look at some polynomial, or rather even at the family of polynomials, where these coefficients depend on this parameter t and change appropriately as t goes to infinity, then these amoebas, the moment you take the limit t goes to infinity, they do converge to a certain tropical curve, which is just a corner locus of the following tropical polynomial. So what happens with your initial polynomial is basically that multiplication changes to addition, and this addition changes to an operation of picking up the maximum. And let me just illustrate this maybe on a simple example of that sort. So you look at certain curve. Here coefficients depend on t, as you see it. Some of them are fixed. They don't even depend on t. And then you look at the following. So you translate all these monomials to terms in your tropical polynomial. So this 1 goes to 0, z goes to x, w goes to y. This term where t is in the inverse 2 power, this gives you minus t here, z squared gives you 2x, and again t inverse gives you minus 1, z and w, which one gives x and y. The last term, which is t in inverse square, gives you minus 2, and w squared gives you 2y. Right? So it looks as follows. So when you look at the amoeba for some fixed t, then it really looks like more or less a biological amoeba. But then when t goes to infinity, it becomes thinner and thinner, and in the end, it approaches this graph, which is called the tropical curve. So, and I even indicated which one of these terms takes the maximal value. So this amoeba switches to the graph, and edges of the graph are exactly the corner locus where the maximal value switches from one monomial here, say minus 2 plus, probably plus 2y, sorry, to this one, or from y to 0, etc. So these tropical curves look like such graphs with certain restrictions on them, and they are related to the Newton polygon, and in this case, when we work with planar curves, this is just a triangle. So as you see, these legs of these amoeba are dual, so are orthogonal to the sides of this triangle. The same here. So this leg is orthogonal to this side, this one to that side, etc. So the Newton polygon, together with its appropriate subdivision, is kind of dual to the curve itself. So the degree of the curve can be seen on these pictures from the number of legs. So this is a degree 1 curve, so it's a line, and in each one of these 3 directions, I see exactly 1 leg. This is a conic, so we have 2 legs going in each one of these 3 directions, which are the direction of the x-axis and the negative direction, y-axis also in the negative direction, and then the diagonal in the positive direction. Okay? So stop me if you're lost already, but actually it doesn't matter. So here are more pictures of tropical curves. So these are more conics, these are cubics. And you see that these graphs, for example, here, it has a loop, and indeed it is related to the genus of the initial curve, of the original curve. These 3 curves are just trees, so they will indeed correspond to curves of genus 0. So tropical curves could be defined as follows. So you can forget everything about the amoebas and just consider them as just graphs in R2, which do have an additional structure. So the first part of this structure is that edges of these tropical curves, all of them have rational slopes, and as I already mentioned, they are perpendicular to the subdivision of the Newton polygon. The next thing is that on each edge, we do have a vector, certain vector assigned to this edge. This vector has integer coordinates. It goes in the direction of this edge. And it has, again, relation. It's related to the edge of the subdivision of the Newton polygon that just obtained from it by rotation. And finally, the most interesting thing is that at every vertex, we do have the balancing condition. So if we look at all edges adjacent to this fixed vertex and orient them outward, then, as I mentioned here, on each edge, I do have a vector in the direction of this edge. So let's look at these vectors and sum them up, and then the sum should vanish. Right? So basically, you can forget everything about amoebas and kind of the reason why these curves were introduced in the first place, and just look at them at some metric graphs with certain restrictions. Right? So, and any such graph indeed is a tropical curve, and the genus of this curve you can see as the genus of the graph. So in particular, trees correspond to rational curves. So it would be good to count these simple combinatorial objects, these tropical curves, again, say passing through a certain collection of points on the plane. But if you count them naively with multiplicity 1 each one, then you see that it doesn't work. However, there's a nice combinatorial rule to assign a certain multiplicity, which is just some natural number to each tropical curve, so that if you count each tropical curve passing through a certain collection of points in general position, then first of all, this number is invariant, and it's even more, not only that it's invariant, it equals to the honest number of complex curves through a collection of 3d-1 points. Right? So, and indeed you can just, this correspondence, make it very explicit to see these rational algebraic curves which converge to each one of these tropical curves. Now, this is not specific only for plane curves, but similar results hold also for other toric surfaces. The only reason is that instead of the triangle, you should look at the other Newton polygons, and they also work in high dimensions. So it's a series of works of Nishino-Zyberg. Now, obviously, you can also ask the same question in many other variations. For example, instead of complex curves, you can ask about real curves of the fixed degree and genus passing through a configuration of real points. And Welchinger discovered that such a count can be done in an invariant fashion. So first it was done on the honest real algebraic geometry level, but then also the tropical counterpart was found. Again, there's a simple combinatorial rule to assign a multiplicity. This time, this multiplicity of a curve is just 0 plus minus 1 for each tropical curve. And then the weighted count gives you the honest Felschinger invariant. Now, a new feature in this count is that it turns out that the tropical technique here is, in a sense, stronger than the classical one. So these weights, which you assign to tropical curves, they also give you an invariant count of curves of any fixed genus. However, in the honest kind of real algebraic setup, when you look at these curves, honest algebraic curves passing through this number of points, this is nicely defined only for rational curves. And there are some other things, some other reasons why this tropical technique is stronger. And the reason for that is that, so first of all, these two weights, the weights with which you count complex curves, or the weights with which you count real curves, could be united in a family of weights which just depend on a parameter, q, which takes some complex values, and each one of these corresponds just to a fixed value of q. This complex case corresponds to q equal to 1, the real case corresponds to q being minus 1, and even more interestingly, this refined count, by the refined count, I mean counting curves with these weights which depend on q. So out of this count, you can also somehow recover some generating series of counting things for the higher genus, log Gromov-Witten invariants with some lambda classes, whatever this is, but they contain also an interesting information not only about rational curves, but also about higher genus curves. So therefore, tropical geometry can be seen as a very powerful tool, which also has not only allows you to recover some known results, but also to get some new results, and all this in a rather simple combinatorial fashion. So there are several obvious questions. So first of all, if you look at this tropical geometry, and you just try to forget about its origin, about the algebraic geometry, and you work just with these graphs, these metric graphs with certain restrictions. That is, a balancing rationality of slopes, integrality of vectors. You can ask about each one of these restrictions. In particular, how important are these rationality and integrality restrictions? Could you possibly start the same machinery and develop this theory when you start from a polygon which is, say, non-rational, right? So here we come to the topic of this conference, and you just look at any polygon now on the plane, and you think about it as kind of a Newton polygon, and just try to develop the tropical geometry. So I will not talk about the honest algebraic geometry analog for non-rational Newton polygons, but just a purely combinatorial tropical or pseudo or quasi-tropical geometrical setup in this case. And then, of course, you can also ask, well, suppose that we manage to find such generalization by dropping these rationality and integrality restrictions, and we try to count curves and with certain weights, then you can of course ask, well, why these weights? Are there any other weights? Because if you already forget about the original setup, the original kind of real or complex algebraic geometric setup, then why not to work with some other weights? And then how to produce these weights, if there are any. And then obviously, can you say anything about geometry, topology, or algebra underlying these weights? Again, without any relation to the underlying kind of honest algebraic geometry, but seeing it only in this version of tropical geometry and possibly some moduli space. So here are some results in these directions. So first of all, we generalize these tropical curves, just totally omitting these restrictions on rationality and integrality, but of course keeping these balancing conditions intact. So these objects would correspond to non-rational polygons. And these are some kind of balanced metric graphs, and we call them pseudotropical curves. So the whole theory is developed exactly in the same way as for honest tropical curves, but the only difference is that now when you look at these legs, they don't have to go already in these fixed standard directions, like it was, say, for the triangle, which correspond to plane curves, but they're allowed to go any directions, and also these vectors assigned to these legs don't have to be unit vectors, say, but these can be any vectors. They're not integer anymore. They just go in this direction of these legs. The only condition which we need is that they sum up to 0 when you sum over all legs of your graph. Apart from that, the whole picture of the pseudotropical curves looks exactly as kind of the tropical curve, except for these removal of restriction on directions and integrality of all these vectors, right? So if you wish, this kind of Newton polygon can be obtained from the set of all these vectors by a simple operation. So you just look at all these vectors assigned to your legs, you order them in the kind of, so that the direction change in a monotone fashion. Then you rotate each one by 90 degrees. Then after the rotation, say from V2, you would get V1 star, which was just this vector rotated by 90 degrees. From V2, you get V2 star, again by rotation by 90 degrees. V3 gives you V3 star, rotated by 90 degrees, etc. And you just follow them by adding one to another. And in the end, you will return to the same point just because the initial vectors add up to 0. And so, of course, after the rotation, they will also add up to 0. Right? So this picture which you get is kind of the dual polygon, or in a sense, which plays the role of the Newton polygon corresponding to this curve. And you could also make sense of its decomposition, but I will not talk about that because kind of the recipe is slightly more complicated. How are we doing so far? Is at least the idea clear?
Very nice.
Okay. So now, what about the existence or uniqueness of these curves when you fix the metrics or lengths of the internal edges? You can actually look at these curves as some critical points of a certain action functional, and they do appear as solutions of some discrete version of a new Neumann type boundary problem. Again, I will not enter here into details. It's too long and complicated. It has to do with some Kirchhoff laws and electric networks, in fact. But it's just good to know that they do exist, and similar to usual tropical curves, you can state some results about their existence and uniqueness, which is all you need to do, without any relation to the algebraic geometric mean. Moreover, all the theorems to which you are used from classical algebraic geometry, they do hold also in this setting, of course, after suitable modifications. So, for example, even it's unclear how, in the beginning, how to define the degree of a curve. And it turns out that now it's not necessarily integer. So what you look at is you just look at the area of your kind of Newton polygon now corresponding to the curve. Well, take it twice. So for the usual case of planar curves, this would be a triangle with sides of size d. So twice it would give you square with each side of the size d, and so its area would be d squared. So you take the square root, and it should give you d. And it turns out that the same thing works also in this new setup. So basically, you just generalize the notion of the degree in an obvious fashion. Nothing interesting here. The only feature is that they're not integer anymore, usually. And all these standard Bezout and Bernstein theorems, they also hold. And you can reformulate them in terms of some Minkowski sums of polyhedra and mixed areas. So again, in rather straightforward way. So it was known, of course, that the Newton polygon contains all the necessary information, and indeed you can do everything you need in these terms. Now, so what's good in these pseudotropical curves? So apart from the fact that you can use them in the setup when you remove the rationality conditions, so it's some kind of irrational polygon or polytope. So there's another feature, and this is the one that it allows you to vary all these parameters now smoothly. Before, you were stuck with some directions which couldn't be changed, and also lengths of vectors were integer, so they could be varied only in a discrete manner. However, now you can vary, say, these delta set of the curve, or these vectors, just smoothly. And if so, it's also very convenient to use the general position considerations and also the limit construction. So you can do a lot by varying slightly these parameters and then passing to a limit. And I will not give examples here, but it actually works, and surprisingly well. Now, then this theory, which we developed initially just on the level of combinatorics, more or less. So the question was, are there meaningful weights which you can define on these curves? And you can reformulate this construction in terms of certain moduli spaces, and this is the moduli spaces about which I will talk more, and the construction of these moduli spaces and its structure gives you the weights. And moreover, so these weights are related to the top homology of these moduli spaces, And it just turns out that this top homology is more or less immediately identified with certain vector space, which is known, say, very well in knot theory as the vector space of Jacobi diagrams. And these are objects which, in a sense, it's just a diagrammatic version of a Lie algebra, where you, instead of writing algebraically certain relations in Lie algebras, encode them by some simple diagrams. So this top homology of the moduli spaces turns out to be related to Lie algebras. And since top homology is related to weights of curves, then weights of curves are related to Lie algebras. So therefore, given a Lie algebra, but just a certain additional data, which I will not mention, there's a nice way to produce the weights corresponding to this Lie algebra. The nicest probably...
Okay, that's what I was going to ask you. Yeah.
So the nicest feature here is that the weights which we know, and these are these one parameter, say, weights, which correspond to counting both real and complex curves, they do appear from a Lie algebra, which is very well known, and it's just the quantum torus Lie algebra. So I will mostly talk about these three pieces. So I will skip the results about these pseudotropical curves. You will have to trust me that such a theory can be developed in a straightforward combinatorial fashion. And you can find it in our preprint with Lanzat, if needed, with all details. But the nice thing is that not only the quantum torus Lie algebra is responsible for the weights, which we know for the simplest passage problem, but also more complicated enumerative problems where, in addition to passage, you also include some tangency problems. It turns out that they're also related to the same quantum torus, but instead of the Lie algebra, now you look at it as the super Lie algebra. So there's the well-known also super Lie part, and it turns out to be related to these tangency problems. Right? So I will try to cover these three pieces in more details. So that would be the plan, right? Good. So, and that we also, it's interesting that apart from the Kontsevich recursion, you can also in this way, because you generalized the set of your initial objects, you can cut them in pieces in some new ways, and that gives you some new recursive relation for such counting problems, which is probably interesting in itself. Okay, so let me discuss these moduli spaces. So I fix the set of vectors which sum up to 0. In a sense, I think about the last, or the first vector v0 as the minus sum of all the rest. I will kind of think about it as the outgoing leg, specifically or root of my curve, but we'll see about that. So first of all, we fix these vectors. So it gives you this Newton polygon, if you wish, which is dual to that. And we'll look at the moduli space of all such pseudotropical curves corresponding to this set of directional vectors on the legs. Right? So this moduli space, which we will also compactify in the process, let's first start from its top dimensional cells. The top dimensional cells are pretty simple. So they do correspond, each one of these cells correspond to a combinatorial type gamma of some pseudotropical trees because we only think about rational curves. We add a certain rigidity requirement. I will talk about in a second. But so you look at a tree, if you wish, which looks as follows. So it should have m+1 legs. All internal vertices should be trivalent, and then it's easy to check that the number should be m-1. But in addition to that, we also fixed marked points, exactly m marked points. They should all be distinct, and they should also be distinct from the vertices. So they're only on these open edges. Okay? So it's a tree with m+1 legs and m distinct marked points. Now, such a picture is rigid if each connected component of my tree minus the set of these marked points contains exactly one leg. So here are a few examples so that you will understand how it works. So this tree with this set of points is rigid. When I cut my tree by these red points and I look at the resulting pieces, in each piece I see exactly one leg. So in this piece here, this will be the leg. In this piece here, it basically consists of the leg itself. In this piece here, it's this leg, right? Now this is an example of a non-rigid curve. It's non-rigid because this requirement that each piece contains exactly one leg is broken. So you see that here there's a component. This is the connected component, which doesn't contain any legs at all. Right? So this can happen. This just happened because I added one additional point. In a sense, if you count the number of points here, this is 5, here this is 6. And that's kind of basically, that's why the reason why we want exactly m marked points when our tree contains m+1 legs. Because if not, it will immediately, this condition will get immediately broken. However, this could also happen if the number of points is correct. So say for this curve, the number of legs is 1, 2, 3, 4, 5, 6. So I should place 5 points. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the number of points here and here is correct. But this curve is rigid, while this one is not. And again, the reason it's not is because here there's a connected component which doesn't have any legs at all. But of course, then there is also the component here which contains 2 legs, too many legs. So these are both problems which come together, no legs or too many legs. Okay? So by some technical reasons, we're only interested in these rigid marked curves. And it's also convenient, just again, for technical reasons, it's nice to fix one of these trivalent vertices as the root vertex. Okay, so then what is a pseudotropical curve of this fixed type? So you can do the following with such curves. So first you can shift such a curve in the plane. You can just take a translation, moving it to the left or right or up and down. In addition, you can change lengths of all these internal edges, right? So leads have infinite length, but each one of these finite edges, these internal edges here, has a certain length, and you can vary this length, right? So a tropical curve of this fixed type is totally determined by all these collection of lengths, and it's easy to check that it's exactly 2m minus 2 such lengths, and the location of one of its vertices. So that's why we call one of the trivalent vertices a root vertex, and we fix its location, right? So therefore, you can more or less identify such a cell with the following space. So R2 here corresponds to the location of the root vertex, and each one of the lengths gives you, all right, yes. So each one of the lengths gives you R plus, and there are 2m minus 2 of these edges. So I just, instead of counting this R plus 2m minus 2 times, I counted it now like R2 plus in power m minus 1. Okay? Doesn't matter actually. So the whole cell is basically the half plane in an open half plane in the mth power, right? So the dimension is 2m. So that's how an open cell looks like. Now, to identify this cell honestly with this Euclidean space, you should fix a choice of these internal edges. And this ordering can be changed by even permutation. So it's called the sign ordering of the internal edges. So another way to kind of order this set and to identify our cell with this Euclidean space is to choose, instead of this ordering, a Lie orientation. And the Lie orientation is just the cyclic ordering of all half edges emanating from each trivalent vertex, and you're allowed to negate any two such cyclic orderings simultaneously, right? So you take two vertices and change two cyclic orderings. So it's the same orientation. And we will call it a Lie orientation by the reason which soon will become clear. And actually, choice of this Lie orientation is equivalent to an honest orientation of this cell. So here I explain this. I will probably skip this. Should just believe me that this Lie orientation honestly gives you an orientation of the cell. It's the proof, but you don't really care about this proof. So skip all this part. Don't pay attention. So our cells comes with orientation, and additionally, each cell also comes with an evaluation map. The evaluation map is an obvious thing. So you just take a curve. It was a marked curve, so it contained m marked points. So you just forget the curve itself and keep only the set of the marked points, right? Marked points were ordered, so this is the mapping into R2 in power n, an honest space. Right? A nice feature here is that this evaluation map is a map between spaces of the same dimension. Right? And moreover, you can actually check very explicitly how this evaluation map works. And if you identify your cell, as I explained, with this Euclidean space, then the evaluation map is just linear. So you really know everything about this evaluation map on each open cell of top dimension, right? Now, this is it for the top cells. Now it's about time to glue them together in a closed space and then to compactify it to get an honest moduli. So we do it in 2 steps. So the first one is just close each cell near 0. So that was, before that was R plus. Now you just look at it as R greater or equal than 0. So you just add the 0 kind of pieces these to it, but you don't do anything with the infinity. So you just add zeros. Now, when you did that, you can glue the resulting polyhedra together along the boundary structure, right? So the boundaries will be obvious here. That's when some of these lengths will vanish and become 0. So you can glue them together and identify these combinatorial types of graph in some very obvious manner that will look like, say, collision of 2 trivalent vertices when some length shrinks to 0, and then there are various ways this could happen for different gammas, and you just glue them together. Okay? So you already obtained the resulting moduli when you glue together all these cells. It is, however, not compact yet, right? Because there are these infinities. There is infinity here and there's infinity here. You could or make some lengths infinite or just shift the root vertex to infinity. But you just naively and I should say brutally compactify it. Just take the minimal compactification. It can be done more cleverly, but you know, if I have a hammer, why not to use it? It's totally sufficient for my purposes. I just brutally compactify it at the infinity by 1 point. Okay, and it turns out that everything is nice, and that the evaluation map now extends to the evaluation map from this compactified space to the sphere. So when some lengths become infinite in the image, you also get the infinity, and I think about this sphere as about the Euclidean space, this one, again compactified by 1 point at infinity. Okay. So now we have a nice thing. We have a compact space, nicely glued together from strata of different dimensions, and its evaluation map to the sphere of the same dimension as the top dimensional strata here. So now let me explain how you can construct some invariant counts. And invariant counts correspond to cycles, to top dimensional cycles in this moduli space. So I look at the top dimensional cycle, forget about this orientation, doesn't matter. I take top dimensional cycle, so it looks like the sum over certain combinatorial types, these combinatorial types with some coefficients. Okay? It's a cycle of dimension 2n. And suppose that I have a collection of points now, and m points in R2 in general position. I would like to count now the number of these pseudotropical curves of a fixed combinatorial type and then of all possible types, passing through this specific collection of m points. And the way to do it is the following. So let me just do this first. I just naively look at the number of these region-marked curves of a fixed combinatorial type, where this collection of marked points, remember that there was also exactly m marked points, coincides now to P under this evaluation map. Right? And I just do it as follows. So this number is not invariant. It will change when I move this collection of points. However, if I sum up them together with certain coefficients, then the total would be invariant. Now, how do we do that? So we fix this combinatorial type. This combinatorial type will be counted with this coefficient. Right? And I count each one of these curves here with this multiple, and I sum up them over all combinatorial types. I just call this number the degree of this evaluation map at this particular point. Okay, so if you wish, I pull back this point by the evaluation map and look at it in my moduli space, or I push it forward. Again, it's better to think about it, push forward classes and the intersection in the sphere with the class of the point. But basically, it's just degree of this evaluation map at this specific point. And it's a feature of the homological intersection number that it does not depend on the choice of this point as long as it is generic. So this weighted number, remember that these weights were picked from the cycle, this top dimensional cycle in the homology. This number is invariant in the sense that it does not depend on the collection P. So it's a nice thing, right? So the moment we will work with these top dimensional cycles, when we will know some cycles, we can construct an invariant count. And moreover, of course, it will also, this number will actually depend only on the homology class of this cycle, not on the cycle itself. I missed this. Okay. So our invariant counts correspond to these homology classes in our moduli space. And so we would like to know what's the top homology. Here I don't have any time, so I just tell you very fast about this. So they correspond to combinatorial types of these reject trees, and the relations come from gluings. And the gluings happen or in triples when some internal edge collapses, or when one of the marked points collides with the triple vertex. So there are two types of relations between our generators. One of them is just some antisymmetry, and it corresponds to this gluing. The other one is that the sum of some three terms equal to 0. And as you probably can see here, they correspond again to the gluing of three different graphs along the common strata where you see a 4-valent vertex. And you can think about this as the Lie bracket relation in a sense. And how do you do this? You think about A entering here, B entering here, and their commutator going out. Remember that there's a cycling ordering. So you take the commutator, and then C enters. And then the commutator again goes out. And here you do the same. And then this becomes just the Jacobi relation in Lie algebra. So it's kind of a diagrammatic version of the Jacobi relation. Okay? That's why they are called Jacobi trees. And this is a diagrammatic version of a Lie algebra. And the moment you start from any Lie algebra, you can construct a cycle on our top homology just because of the relation of Lie algebras to this space. So the nice thing is about these quantum tori Lie algebras, and here I just have basically probably 2 minutes on that. And you just look at the quantum torus, which is well known. So you look at generators, you just fix an abelian group. You look at them, this abelian group, this is just the lattice generated by vectors from the set of your vectors on legs. So before that was kind of the standard Z square lattice. And you look at the bilinear form, which is antisymmetric, which is just the cross product of these two. So the vector product, the cross product, which is the determinant of these two vectors. So, and then you define the multiplication in this way. So up to the certain multiple, this is just the addition of these two vectors. And the multiple here is what it makes it non-commutative. Right? So that's this H bar is the quantum parameter. And for plane tropical curves, this is the standard lattice Z square, and this is the well-known standard quantum torus. So the Lie bracket is, of course, defined as in an obvious way. So the bracket is just the difference between L alpha L beta and L beta L alpha up to a certain multiple. And it does not matter which multiple you choose, they are all the same. You can normalize it nicely, and then you get this Lie algebra, which is known as the quantum torus algebra. And this thing here is the so-called quantum numbers. You probably know quantum integers, but you can do that for any h, and you do that, right? So, and you check that that this bracket indeed gives you the Jacobi identity, and then there's a simple procedure for which I failed to find any time. Sorry. To construct a weight starting from this quantum torus Lie algebra and the set of our vectors. Basically, you put these vectors on the legs, so you assign all these elements on the incoming legs, and then you go along your tree, and when you pass a trivalent vertex, when you have two incoming edges to the outgoing edge, you assign the Lie bracket. And then on the outgoing root leg, you have this vector up to a certain multiple. And this multiple is just the weight. Okay, so whatever this is a totally standard procedure. And so this gives a cycle in the top dimensional homology, and therefore an invariant count. So here I more or less stop. I just say that for usual tropical curves, these weights are exactly the refined weights of Bloch and Götzsche. So these refined weights of Bloch and Götzsche, again, they correspond by this simple procedure to exactly this Lie algebra of the quantum torus. somehow the fundamental reason for that escapes me. I can say some guesses, but it's problematic. However, at least it's true. So here I stop. Thank you.
Well, thank you, Michael.